But I'll record what I'm supposed to tell you and I'll keep it on Moodle. So it's basically what I'm going to record will be spice simulation. So for spice simulation, there are two ways to do the simulation. Either you draw the schematic entry. So all the things which we have done till now, it's known as schematic, like this inductor, capacitor. If I'm doing this, it's a schematic entry. But if I want to do something else, which is called netlist. So in reality, all the simulators are going to take everything in terms of some netlist. Netlist is the one which is going to keep all these elements at appropriate place uh, using using some way of writing the simulation. So if I want to write down that inductor is between V1 and V2 voltage, let's say. So I'm going to write down that inductor, first of all, the name of the element, then its symbol, and then I'm going to write down V1, V2. And this is the meaning of, so this is netlist for this particular circuit where I'm going to write down L equal to maybe 1 millihenry. Maybe next one is capacitor, which has a value which is C, which is between V2 and 0 volt, whose value is, let's assume, 1 microfarad. Actually, you don't have to write the units, right? Dinesh, is it right? So we don't have to write the units here while doing this net listing, CO2. And afterwards, you have to define V1 because it will have some sine wave. So you have to add the sine wave here. Similarly, you want to do some transient analysis. So transient analysis with some value, maybe for till 1 millisecond you want to do it. If you want to do some AC analysis, all this dot is stands for analysis which you want to do. And before all these things, you need to define this L is inductor or C is capacitor, whose model means how the voltage and current equations are linked with each other. It will be written in some model library file. So that is how netlist is being made. I'll share one elaborative example where you are going to be taught to make some spice simulation using some op-amp circuits. So when I'm going to like teach you through that video lecture, what you have to do, I'm going to give you project, one project per person, where I'm going to share one circuit with you. So there will be one circuit. That circuit might be circuit which is based on op-amp, and this will be some filter circuit. It might be third order, fourth order, fifth order, anything. Circuit will be given to you. And by looking at its schematic, you have to write the netlist. And through netlist, you have to simulate it, and you have to share the results, and you have to like show me those results. On the basis of that, I'll give you marks. So that project is of 10 marks. So this will be useful in your future for any course. Might be power electronics, people are using more for such things. So if you're studying something power electronics, or some communication people are also using, and all the VLSI engineers, they are also using every day such things. So this will be useful. This is just one exercise so that you can learn how to write the netlist. This whole process is known as netlist. And then you can simulate it. So it will not be schematic entry, it will be netlist entry, which you need to do. So this is what I'm expecting from you. So if it is third order, if I have given you third order, with some values are also already given to you. So you may get this kind of response. So as a conclusive remark, you have to say that what is the gain you have achieved, what is the gain bandwidth, what is UGPW, phase margin, all these things you have to write down by plotting this thing using Spice. So this is what I'm expecting for this project. So mostly before weekend I'm going to keep this Spice simulator video. Is it fine? Because it is becoming difficult to meet and teach you. But if you wish, we can have some extra lecture where I can teach you Spice. Whichever way you like, it's okay. Do you want video or do you want to meet? It's single person, like everybody has to do it. There is no escape. Right? Everybody will have different circuit. I can find out, like there are 45 circuits. It's very easy to find out 45 different filter circuits. Right? So I'll give it to you. And everybody has to do it before certain deadline. Okay. So last time we did this continued partial fraction, and we got these particular values. So if I have 2s 5 plus 12 s cube plus 16s divided by s raised to 4 4s squared plus 3, then using continued partial fraction method, note that this is the method which we are doing to find out equivalent coir 1 form of LC circuit. We have already learned what is Foster 1 and Foster 2. In Foster 1, we have made impedance function. In Foster 2, we have admittance function. Foster 1 is also known as series and Foster 2 is known as shunt or parallel. Similar to that, coir 1 is LC and coir 2 is CL. LC means first element will be L and here first element will be C. Okay, so if I write this entire thing, it will be equal to 2s divided by 1 by 4s plus 1 by 8 by 3s plus 1 by 3 by 4s plus 1 by 2 by 3s, right? By this continued fraction method, I can say this, right? Do you have any doubt in this? Sohan is here or? Okay, Sohan solved this last time and he got this answer. So can you draw the equivalent circuit for this function now in your notebook? Mahima tried that last time, right? Last time. So you can draw this. So first element, by the way, this is impedance function. So first element is impedance, so it will be inductor or capacitor. So this is an inductor. Let's make all the green entries as inductor and blue entries with capacitor. What will be 1 by 4s? Why inductor? This is admittance now. So 1 by this one is capacitor. If you are looking at next entry, so this was impedance, this is admittance, so this is 1 by, so this is impedance. So in impedance, you are going to see this one as capacitor or inductor? Inductor. This is impedance, so this is admittance, so 3 by 4s is inductor or capacitor? Capacitor. You can easily guess that it's LC circuit, so LC should be coming, right? Why? Oh, 1 by 4, okay. It's not in denominator. Maybe you are, so if you look at here, it's S is not in denominator. It's on numerator. Okay. Maybe the way I have written is confusing. So all these S are in numerator, right? So this is L, this is C, this is L, this is C, this is L. When you are drawing this L, so remember impedance function, if we have plus sign means first entry and the second entry will be in series. But next is capacitor, but the next entry should be in shunt because this is plus entry for admittance. So inductor, right? This one, third one. First one was 2 Henry, 4 Farad, 8 by 3. Oh, this has to be 1 by 4, right? So after this will be in series, right? After this inductor has to be, right? If you redraw the same thing, so you don't need to do this exercise every time. You can see directly, you can see that it's inductor, capacitor and inductor. The last capacitor is not there, so this value is 2 Henry, this value is 1 by 4 Farad, this entry is 8 by 3 Henry, this is 3 by 4 Farad, this is 2 by 3 Henry. Then there. So if coil 1 form is already asked, so you don't need to exercise such thing every time. So if Foster 1 is asked, if it is LC circuit, we know that Foster 1 is always series and the first element might be inductor or capacitor, and thereafter the shunt combination of inductor and capacitor will get repeated, right? And then this Foster 1. Foster 2 is parallel combination of LC, so I can make first entry as either inductor or capacitor, but rest of the entries are inductor and capacitor in series, but they are all in shunt, right? Similarly, coil 1 has first entry is L, second entry is capacitor, inductor, capacitor, and so on. For coil 2, the first entry is capacitor, inductor, capacitor, inductor, and so on. Now let's assume that this circuit is not LC, but if I am telling you that this circuit is RL, so this circuit is RL. So what difference I am going to see? X0 you may have resistance or inductor, and it's a parallel combination of inductor and resistance, inductor and resistance. And same way here, it's RL, so first element will be resistance RL, and similarly L and R, right? So this is just to remember how to do it, and same thing you can do it for RC, replace all L with capacitor, right? So this is the final answer for what we were doing. So if somebody is asking you to find out coil 1 form for LC circuit, then you have to apply continued fraction expansion. But if somebody is asking you to find out using Foster 1, we are not going to follow this continued fraction expansion, but we are going to follow the partial fraction. For that you may use residue theorem, right? Okay. So is there any difficulty in this kind of function? So now I am moving to next, which is coil 2. So if coil 2 is asked, note that coil 2 is also impedance function, or it might be admittance function. There is nothing like Foster 1 is impedance and Foster 2 is admittance, but the writing part is different than what we were doing in coil 1. In coil 1 we were starting with the highest order. So for solving coil 1 we used to write down equation this way and we used to divide it. However, in coil 2 form, we are going to write the equation from the lowest entry and then we are going to divide. So 2s by s cube, this 2s by s cube entry will divide 3 plus 4s plus s raised to 4. My mistake, right? So it will be divided by this one. Can you solve and are you getting same entries? Can you check that? Try once. This is the last example for coil 2. So Akshita, things are going fine? No? By the way, anybody know about Nyquist rate? Nyquist? What is Nyquist rate? Okay. So you are saying that if there is a sampling and you have to do it at least more than twice samples, right? Right. So sampling frequency greater than or equal to 2 Fin. Right. This is what you used to do. The sampling theorem. Right. You studied this. So what is happening with Akshita? She is not sampling all my lectures. So she forgot to sample one lecture. So she is asking others. Previous slides. Okay. So you have to solve from the lower order of Laplace operator. Desraj, are you following? So for this, you need to multiply with 3 by 2s, then 4 by 5s. I can write down same function as 3 by 2s plus 1 by 4 by 5s plus 1 by 25 by 2s plus 1 by 5s. Right? The same function I have written in different way. So now all these Laplace operator are in denominator. They are not in numerator. So the first entry will be capacitor or inductor. Capacitor or inductor. This is capacitor. Second entry, is it capacitor or inductor? Inductor. And similarly here, this will be capacitor and this will be inductor. Right? So when you are going to draw the circuit will look like this one, where you have to keep all these units in capital. Is it okay or is it fine? No or yes? Why no? Okay, so tell me what you could not. Okay, why we are doing this? That's the question, or you don't follow the process, or process is fine. Okay, why we are doing it? Okay, so we are doing it for one reason, that when we have started and I have given you some impedance function or admittance function to draw the circuit, you didn't get the unique answer, right? So there are two different scientists came, Foster and Coyer. They told that we have some way to find out unique circuit, and those unique circuit will have name Foster 1, Foster 2, Coyer 1 and Coyer 2. Foster 1 is series and it's going to synthesize Z of S. Foster 2 is admittance and it's going to synthesize for parallel circuit. Similarly, Coyer 1 and Coyer 2 are the one where here the first element will be L and second will be C. Here C and second will be L. Just to make that, he made the continued fraction expansion, but one time he is dividing normal way and one time, sorry, not this one. Yeah. One time he is starting with higher order and one time he is doing same process with lower order. So in one case he get all the multiplying numbers where uh, where your Laplace operator is in numerator, and in another case it's going in denominator. When it's going in denominator, this becomes first entry as capacitor and second as inductor. If you look at here, the first entry is inductor, second entry is capacitor. This is one way to draw the circuit. You can choose any one of them. No, output will be same. So if you are looking into this, if you look at the Z of S using Z parameter technique or any parameter technique, you are going to see what is written here. You will get this answer only. So it's a different way to synthesize. Right?
These four ways help us to make a unique circuit for a given transformer.
Yeah.
So you said there are other techniques also, but there is no unique solution. That's the reason.
There are others also, but we are naming them.
So does this ensure that if we use this technique, we'll be needing a minimum number of devices?
It's not confirmed. It's not. Right. It might be more. Right. So on the basis of your application, you can choose any one of the technique. Right now, what techniques have been given are only and only for passive circuits. Look at this. These are only and only for passive circuits, and these are used to design a system which might be fourth order, fifth order. You look at these transfer functions. So those driving point functions might be transfer function, and it will implement some filter design. Right? Filter is the one which will remove unwanted signal, or it will allow some band of frequency. Let's assume that you are designing a notch filter or band stop filter, which looks like this one. So this slope and this slope, we want, let's say, 8th order will give you 160 dB per decade. Right? So this needs 8th order. So you need to design some driving point function where the denominator entries will have s raised to 8. But you can design it maybe on paper mathematically, but who is going to design the circuit? To design the circuit, you need to use such technique, and you will have the circuit now. And you can implement those circuits to get the required transfer function and required frequency response. Because that is what your main interest. We are doing everything for getting the response as per our requirement. This is what we are doing. So these are the like 4 techniques. But nowadays, who cares about passive circuits? If you search for operational amplifier design on Wikipedia, so most of the invention have been done during Second World War. This was designed for Second World War, operational amplifier. Before that, that was not available. So this Foster 1, Foster 2, Coyer, all these people didn't know that there is something called operational amplifier. So they were working only on RLC circuits. But in reality, we wanted to use operational amplifier, which is an active element. And that is the next chapter after this, design of active filter. Right? So there are few more people came, like Selen and Key, and there are many other people who gave their own technique to design filters using operational amplifier. So that is what we are studying. So we have started our journey from maybe in the 18th century. Then we are in 20th century, and now maybe afterwards we will reach 21st century. Right? So we are studying from fundamental study we have to do. So that is what we are studying one by one. Maybe Foster 1, Foster 2, hardly some people will use, but it might be useful in some place. You should know that, because still these 4 are the standard technique for synthesizing any RLC circuit, which is just passive. But if it is active, you need to use some different technique. which we are going to learn, right? So any doubt now, Gaurav? So this is a end of topic called LC circuit. If it is a circuit which is LC, you need to look at the properties of LC, which says that all the poles and zeros has to be in left half plane. That that roots will be simple, means they will be on j omega axis. There is no real part. It will be always simple. It will be positive real function, right? And third one is they will be alternate or interlaced. So if you look at this transfer function, start with 0, 1, 2 and 3, they are interlaced. So with this transfer function, you can say that I can synthesize this using LC circuit, right? So this will not be told to you at the beginning. Maybe I'll give you some transfer function and you have to synthesize it using LC, RL or RC. You have to find out that through the property. So this is the property through which you can find out this is LC. So I'm going to use LC synthesis with Foster 1, Foster 2, Coir 1 or Coir 2, any one of the technique. But same technique is available for other circuits also, like RC and RL. So Foster 1 is also available for RC. It's also available for RL. Right? Is it fine? Sorry? Different ways. Foster 1, Foster 2, Coir 1, Coir 2, all are dealing with the same transfer function. 4 different answers for same transfer function. Yeah, so you can convert impedance into admittance and then you can synthesize it. Right? So that is also another way of synthesizing the solution. So that is what right now has been taught. Right?
Can you repeat, sir, why
By
saying the transfer function?
saying transfer function.
Which elements we have to use, like LC, RL, or?
Okay, so first thing we have studied is LC, whose property says that poles and zeros has to be on left half side, right? Then those poles and zeros has to be simple. When we are saying simple, they have to be on j omega axis, including 0, right? 0 frequency, and they have to be, of course, positive real function. And these inductor and these poles and zeros has to be alternate. If they are not alternate, this might not be synthesized using LC. So this is the first property we learn. But by looking at maybe if I am going to give you some function which is like this, if so, which are the components do you need? Resistor and yeah, if this is Z, then it's a resistor and capacitor, right? So it's all depend how you are keeping these values. But here you can see that the roots of these poles is only -2. It has real part is also there. So whenever you have real part, it signifies that you are going to have resistive element, right? But if you have something like this, then it's plus or minus j root 2. So this entry is coming exactly on j omega axis, which gives us information that this entry will be LC. Right? So I am going to synthesize using LC. And at the end, we are going to learn something called, just one question will be there where we are going to solve RLC circuit, which will have everything. Right? But still, all the solutions are not unique. You may have even 5th category where you can give your name. Right? If you can think about some systematic approach. Sorry, I forgot your name. What's your name? Huh? Ujjwal. So you can call that technique as Ujjwal 1 and Ujjwal 2, or maybe Ujjwal 3, 4, 5, 6, whichever you like. And you can publish it and you can take the patent. If it has to be like some systematic way, look, right? Still it's a like open question and you can do that. If you have some technique, like Foster 1 and Foster 2 are based on partial fraction method and residue theorem. Coir 1 and Coir 2 are on the basis of continued fraction expansion, right? So you can give some technique, some mathematical technique through which you can synthesize it systematically, and every time answer is same, then you can do that, right? Or you can think about some RLC technique also, or RLC. So that was end of one topic from the chapter 11, where so still I am continuing that chapter where topic 2 is either you have RC impedance or RL admittance. So look at this carefully. This is RC admittance. This topic is RC admittance and RL admittance, right? So RC will be written in Z form, and whenever you are going to see same thing in Y form, it will be RL admittance. Okay. So now let's write something in terms of Foster 1. Foster 1 says that it's a series form. If your circuit is R and L, then I'm expecting either resistance at zero frequency or inductor at zero frequency, or maybe one of them will be at infinity, accordingly like which one is available at origin. So either you will have DC quantity. This will happen when the numerator order and denominator order are same. If they are same, then you will have one entry which is available at DC or zero frequency, which is resistance, right? Similarly, you can also find out inductor. If extra like order of numerator is one time higher than denominator order, then you can say that there is when zero is available at origin, means you will have inductor, right? And other things will be in series, where you will have resistance and inductor in shunt. So this is what Foster taught us, but instead of capacitor, we have kept resistance, right? So this is Foster 1 form of RL. Similarly, if I wish to make Foster 2 for RL, I'm going to have all the entries in parallel. Right? So that is what written here. If you have some impedance function is given to you, by the way, sorry, we are making RC. I made mistake here. It has to be RC. But it's same for RL Foster. So in this case, if you want to find out whether capacitor is there or not, you need to see the denominator order has to be one time higher than order of the numerator. Right? By looking at that, you can find out there is one extra pole available at origin that will transform to the capacitor. Right? But the only problem here is same thing if you are doing with so RC series synthesis using Foster, which is known as foster 1, which is being done for impedance. So that is easy to do with capacitor. This will be resistance. Value of capacitor is 1 by K0 farad. This will be K infinity ohm, and there will be resistance, capacitance, resistance, capacitance, right? But if this function is not Z, if this is Y of S, can you draw what is going to happen? And following my question, so I have synthesized the circuit which was written Z of S. Can I synthesize the circuit if this is not Z of S but it is Y of S? Desraj, are you following or no? So your sampling is very poor. That's the problem. We are meeting almost like second or third time, right? In the entire semester. Anyway, so anybody else? Okay. Yes. Who is behind Manpreet? Yeah. Can you see Dhruv? Okay. So, can you read what is written here? No, no, this one, green colored new entry. Huh? No, we can check how much power is there, how many lines you can read, right? Okay, so who is next to, like, yeah, can you draw this circuit on board? Can you try? Okay, please try in your notebook first and then draw on board. Yes, Ujjwal, are you following, right? So can you draw the circuit which is for Y of S? Can you try here on board? Please. Can you? Dhruv, you should sit maybe on the first row, right? Not so much far. You can see that TV also. Yes. So Nikita, first element is inductor or capacitor? Okay, inductor. Second element is resistance or okay. So what is happening here? We can keep this one side. Y1 of S equal to K1 divided by S plus sigma 1. So that is equal to 1 by S by K1 plus sigma 1 by K1. Sorry? Oh, so yeah. Yeah, that's correct. Okay, that is fine. Enough. Okay, thank you. Okay, so all are getting same entries, Arun, or some different thing? Okay, so here you can see that when we have started with the name of the topic, we have not told that we are studying LC circuit, but like we have told that earlier that we are studying just LC circuit. Here we are saying that we are studying RC and RL together. So if it is impedance, that is RC. If it is admittance, it becomes RL. So this function is generalized function which we can to uh, use to realize foster 1 using partial fraction method, right? So if some transfer function is given to you, you can write it down in the form of partial fraction, where k0, k infinity, k1, k2 all are residues. When you are doing this, if this function is impedance, it's realized using RC, and if it is admittance, it's realized using RL, as drawn by Ujjwal, right? So that's why such technique or such topic we are going to call it RC impedance or RL admittance, right? Okay, this is what already we did. So its major property is already known to us, that they have to be real, it has to be negative side, all these things are known to us. It's similar to what we have studied in LC, or similar to what we have studied in positive real function. So it will follow those two major properties, where one says that all the poles and zeros has to be left half plane, other says that if you are solving the residues, they have to be real and positive. So if they are coming negative, so if they are coming negative, then you have to do something else. It may not be uh, RC admittance, sorry, RC impedance or RL admittance. However, let's make this underlying thing, that in RC admittance, your residues are coming real and negative. So that's the only different property, and that's why I kept it here. So all the residues in the case of LC and RC impedance or RL admittance, residues will be real and positive. However, in the case of RC admittance or RL impedance, you are going to see those values will be real but negative. So that's the last part. We are not going to talk right now, as we are studying RC impedance or RL admittance. So that might be case 1, that is ZS at the 2 points where the real axis and imaginary axis are intersect, namely sigma equal to omega equal to 0. This we are going to call, you are dealing at DC value or 0 frequency. So through that you can find out whether your system has resistance or not. The first element is resistance or not. To find out that, you just have to look at the numerator and denominator. If the order is same, then you are going to observe resistance at 0 frequency. It is written some addition of so many resistance, but you are going to have so many resistance. And similarly, if you are designing RC admittance, then there might be the case that if numerator has one extra entry than denominator, sorry, it has to be reverse, then you are going to observe pole at origin. Pole at origin in impedance function means it's going to give you a capacitor. No, 1 by in impedance. In impedance, you are going to see capacitor, right? Okay. So this is same thing. Which one is present? Which one is not present? And one more thing, if you are looking at two cases, Z available at 0 frequency and Z available at infinity frequency, Z0 will be always higher than Z of infinity if you are designing RC impedance function or RC admittance function. This is going to happen. We can see how this is happening. And yeah, one more thing I forgot to tell you, as a property part, where we had two major properties, but actually there is third, which is not major right now, because we believe that the poles and zeros in all the cases has to be alternate. If they are not alternate, we cannot apply all this theory for Foster 1, Foster 2. It will not work, right? So here you can see that omega 1 sorry, sigma 1 has to be lesser than sigma 2, has to be less than sigma 3, and has to be less than sigma 4, or maybe reverse. Something like you can exchange omega 2 and omega 1, right? You can find out. Still it's alternate, right? The positions are alternate. So we have to remember that these poles and zeros location has to be alternate. If they are not alternate, this will not work. Right? If I am writing z of some sigma, then I can replace Laplace operator with sigma. That's sigma 1, sigma 2. Now I am interested in making the, earlier time we were making reactance curve. If I am interested in finding out impedance curve, where y-axis is z of sigma, x-axis is frequency of that value, then at zero frequency you are going to see sigma 2 sigma 4 divided by sigma 1 sigma 2. That's the first point. And you know that all the frequency, sorry, it's a DC value. It's a DC value or zero frequency value. Similarly, you can keep sigma equal to infinity, and you can also find out what is at infinity. Can you find out what is z of infinity, by the way? If I replace sigma entry with infinity, 1, right? It's 1. So, but this is happening at infinity. So infinity pole is somewhere here, and so that's why this point is not reaching 1, but it's little bit lower than 1, because infinity has not reached yet. So if we are drawing this, then it's 1, exactly 1 at infinity, right? There are two positions where this impedance function will be exactly 0, when this sigma equal to minus sigma 2 and sigma equal to minus sigma 4. Both the places it's 0, and other two places like sigma 1 and sigma 3, those are pole. You are going to observe infinite value. So you can draw the way we were drawing in LC, right? So this is the impedance curve, how it follows, right? So is there any problem till now? Then yeah, it's in left half, because all these entries will be on left half. Sigma equal to minus sigma 2 is 0. So this is the left half plane. Although it's written plus, but they are actually minus. The location is minus sigma, but we are drawing in left half side, or maybe uh, actually it's written clearly, it's minus sigma entries. So that's why all are positive. It's just a notation given by like, because minus notation, it's confusing, right? So is there any problem in till now, Rohit? Hmm. Okay, so it's a mathematical proof. So I am not going right now into that. Otherwise, we can. This will happen if they are interlaced. One more thing: if sigma 1 is lesser than sigma 2, so then it will not work. Still they are interlaced. Then you will make RL circuit, not RC circuit. That's the thing. What you are saying is, when you are going to make the circuit, both are equal, then first thing you need to see the resistance, right? Or maybe, let's look at, where is that? Okay, so first element to be pole, it has to be, make sure that numerator has to be higher than, sorry, numerator has to be lower than denominator. Right? If it is equal to, then just the resistance. So thereafter, all these entries are R and C, It is only possible when we are starting with sigma 1. The numerator entry is lower than denominator entry lower than numerator. Otherwise, it's not going to give you RC circuit. In the partial fraction, if the sigma 1 is not lower, then you are going to uh, make the circuit with RL, not with RC. I'm trying to answer what you are questioning for impedance function. Okay. This is one case. 1 is lower than 2 and 3 and 4. But instead of this, if I do this one, still it's alternate, but it cannot be realized using RC circuit. It will not be realized using RC. By looking at mathematically, you can say that. It's not written anywhere. That's the thing. It's a condition for RC circuit, RC impedance circuit. That's true. I'm not going into the derivation because derivation is not so much important right now. Otherwise, we will not complete the course. That's it. Because some of the interesting part is also there, which we will not able to learn ever. One chapter after this. So tomorrow we are going to complete RC, RL both, right? And thereafter there is one chapter called filter, which is of three lectures. So is it good enough? I cannot cover only one circuit called polyphase circuit. This will be useful all power electronics people, which is missing 2 lectures, I should say. But what you learn was enough or more than enough, then fine. So till now we have taken almost like, this is 30th lecture which I am recording, right? Other than that, you have done 3 assignment exam, 1 laboratory, some surprise quizzes, right? So if you add all together, I am reaching almost 41 lectures. If I am adding all together, it's 41 lectures I am taking. Like adding next complete week and maybe one more day. Right. So completion of this course is almost like more than 90% or 90 to 93%. Okay. Any other question? Like you came before you came, I was telling that all the first 5% people will get O, 10% will get A, and like many need to see, right? So the only thing is first topper is having 53 and next is 46. If this same gap will be there, I'll not be able to give like O to both. Although as per 5%, it's 2. I can give O to 2 people, but you have to decrease this distance, or somebody has to come from bottom.
But if it is 5%, it is 5%.
No, it's not going like that. So this is 5%, and there is some marks also, right? It's not just ranking. It's not percentile.
With a benchmark, like
Yeah. So this is given as per the grading scheme of IIT Mandi.
you are saying, like
Above 5% is not possible.
No,
This is a maximum which is
above 48 marks if someone gets, then 5%. Then 5%.
no. I'm saying right now out of 56 marks of evaluation, the first ranker of the course having the total of 53. Next one having the total of 46. The difference is 7. If I am giving O to both, so then like next guy is at 46 again and then 45. So what about these people? This is one thing. And like this is a like significant gap, 7 marks. Maybe at the end this marks gap will be 10, or who knows, it will be just 1 or 0, or maybe exchange of the position. I don't know. It's up to you people, right? You know where your rank is, and I am going to give this grading, I kept some color coding this side. You can see clear cut some color coding is there. So it signifies the grade. If you want to jump from one grade to another grade, you can do that. Right? This is a rank, the maximum. So afterwards, still 44 marks are left. Look, as per marking scheme, some of the people are getting F grade, but still it is given from O, A, B, C, and D only. You can see that. I have not given E and F. But as per mark, if you are looking at this side, rank side, it's fine. Rank wise, I can give this grade. But for mark side, there is a problem. Yeah.
So you will give up to D.
F also. Right now, there are some people who are getting F. So that's what I was giving the warning to them that still you have 44 marks, right? So the lowest of our class is 12. He needs another 23 marks to pass. From 23, there will be 4 marks of assignment, right? 10 marks of project. If he is getting 14 out of 14 here, then he need 9 marks in end semester exam out of 30. 30, 30. No, it will not be full syllabus. It will not be full syllabus for sure. Huh? Yeah, after mid-sem. Okay, after mid-sem. Sorry. You just write me mail. Look, I don't have problem. I don't have problem. But